Okay, so let me begin to thank everybody for attending. Once again, this is the online SPICE-SPIN+X seminar series organized here by Spin Phenomena Interdisciplinary Center that Guy and Eversociety and I lead here in Mainz, and the Collaborative Research Center with SPIN+X, whose speakers are Martin Schliemann, who has joined us today, Burkhard Hillebrand and Matthias Chloe. And these are, as usual, are Zoom webinars, meaning that you will be, these attendees can see the talk as well as whoever is speaking, but you cannot see the other participants. But you can ask questions during the talk. Please leave them written there such that I can then afterwards pass along your microphone so you can talk to the speaker directly and ask your questions. And if there's some urgent question, I can also stop the speaker, but usually I will wait until the speaker is finished, in this case, Libor. And as usually, the talks will all be every talk Wednesday at 3 p.m. Today, we had a switch from Christian back, which had an emergency, that had to be attended to. And then we have Libor Šmejkal from Mainz University talking about the recent prediction and discovery that we've had. And since he actually gave a talk last night in the other seminar series that is parallel to ours in the US at that night, we thought this was the easy solution to also share with a different audience this one. And then next week, of course, we have Ingrid Mertig, and afterwards Burkhard Hillebrand. Let me say a few words about Libor. Libor is a very special person within our group. He was a student of Thomas Jangworth and myself. Both graduated very recently from the Czech Republic Academy of Science from Thomas, but was here also in Mainz during the time since 2014, and has been really one of the leading young scientists in topological antiferromagnetic spintronics with very interesting predictions, and in particular one of the crystal Hall effect that he will tell us about. And he's also going to share with us some recent observations that we believe are showing that phenomenon. So with this, I will stop sharing, and I will ask Libor to go ahead and share your screen, and start your talk whenever you can.
Thanks, Jairo. Thanks a lot for the introduction, and also I enjoy to, on the few days' notice, to give a talk. I like to give talks under pressure. So, as Jairo said, I will talk today about crystal time reversal symmetry breaking and spin splitting in collinear antiferromagnets. And that's the work which we were doing together with Jairo, Tomáš, Rafael González Hernández, and Zhikui Liu for the last couple of years. And for those who, for instance, saw the talk yesterday and want to just take home message, I have just this simple sentence, and that's it. So what I want to explain today is that in certain collinear antiferromagnets, you can obtain spin densities which are looking like this. So they are highly anisotropic, and they might generate some interesting physics, namely, for instance, spin-conserving spin splitting and new types of spontaneous Hall effects. So mainly I will be talking about these two recent papers. This is a paper which is theoretical prediction, and this one is joint experimental and theory effort on observing this effect. So let me start with a brief introduction. Talking today a lot about energy bands of solids, which are generating many interesting functionalities. And one of the most famous example is Dirac cone, which was found in graphene and in topological insulators. So you have energy and crystal momentum dependence looking like this Dirac quasi-particle. And then you have there also this spin texture, which looks like Rashba spin-orbit interaction. So people were very excited in the last 20 years about these systems because they are offering suppressed backscattering. And when you add some sort of magnetism, you can separate the spin channels, so you have quantum anomalous Hall effect. However, these systems still have some disadvantages, and you obviously need heavy elements because you need large spin-orbit coupling for the band inversion and also for these textures. And then you have also screening from other trivial states in these complicated systems. And when you are trying to make them magnetic to not spoil completely the topological protection, you are constrained to diluted fragile magnetism. And this altogether is limiting these effects to be observed only at the millikelvin or Kelvin temperatures at the present results. So if you want to know more about this area, there are some recent reviews. Another interesting research area which emerged in the last 10 years and is based on relativistic physics is antiferromagnetic spintronics. And there I would say was one of the main discoveries in the last couple of years that the antiferromagnets, which were commonly very difficult to be controlled by magnetic fields because of the exchange enhancement, they can be now controlled by electric currents. And the idea, again, is working, for instance, based on relativistic physics. So once you run a current through antiferromagnet with some specific symmetries, the local spin polarizations induced by the electric current will have again a form of this Rashba spin-orbit interaction in a symmetry of antiferromagnets like copper manganese arsenic or manganese 2 gold. And this symmetry and the microscopic electronic structure is then producing a reorientation of this antiferromagnetic vector. So this is a beautiful result because now you can hopefully improve scaling of the devices based on these systems when you compare to ferromagnets, because you don't have dipolar fields in antiferromagnets, and also you can promote faster speeds because instead of gigahertz in ferromagnets, the intrinsic antiferromagnetic resonance in antiferromagnets is at terahertz scale. However, because these systems are metallic, you still have a limited signal magnitude, you have dissipation, and you need quite strong currents to reorient these systems. And also, inherently, because you have large spin-orbit coupling, you actually are producing spin decoherence. So the spin-orbit coupling is at the same time friend and foe because you need it to produce this relativistic physics, but at the same time is killing your spin quantum number. So we tried in the last couple of years, found a system where we could combine the advantages of these two research streams. And it turns out that actually antiferromagnets might be feasible candidates. And one of the simple reasons for that, why they can be so successful, is that they materialize in more symmetry groups. So if you look at all 1,651 possible magnetic symmetry groups, you will find that the non-magnetic systems, like in the topological insulator case, are only 230 types. Then the ferromagnetic types of the conventional ferromagnetic spintronics, there are 275. But in the case of antiferromagnets, you have almost one order of magnitude more possibilities. So you have 1,421 antiferromagnetic symmetry groups. So you can imagine that you have a wider playground what effects you can then produce with the symmetries. And I will be talking about one particular consequence of this wider playground today. And there are several reviews on this topic, and it turns out that the systems, these topological antiferromagnets, can actually offer large signal-noise ratio, lower dissipation, while having still robust intrinsic antiferromagnetism with high critical temperatures. The dynamics is ultra-fast. There are no stray fields. In contrast to intrinsically metallic ferromagnets, you have available semiconductors and semimetals in antiferromagnetic classes, and this leads to realization of some exotic and quantum topological physics. So this brings me to overview of the specific consequence of this symmetry analysis, which I will be talking today about, and that's this crystal time reversal symmetry breaking. So I divided the talk into two parts. In the first part, I will introduce a little bit technical aspects of the magnetic symmetry analysis. In the second part, I will focus on the prediction of this new spin splitting in ruthenium dioxide collinear antiferromagnet. And then in the last part of the first section, I will summarize and compare this spin splitting with more conventional spin splittings in Rashba non-central symmetric systems. In the second part, I will then focus on one consequence of this spin splitting, which can be observed experimentally and which we observed together with Jikwi experimentally, and that's this crystal Hall effect. So I will talk about introduction into the spontaneous Hall effect physics. Then I will talk about this particular crystal Hall effect in ruthenium dioxide antiferromagnet, and then I will summarize what different signals can actually contribute to spontaneous Hall resistivity in antiferromagnetic systems. And to let me start the results, I wanna mention that actually the symmetries I will be talking about, they have this specific toroidal symmetry. So when you take this magnetization density and you rotate it by 90 degrees and move it here, you see that it behaves exactly like these swans. Okay, so by rotating by 90 degrees and moving them and recoloring them, you change one to the other. And that will be one of the important symmetries playing a role in the spin splitting. So the effect itself, because it can be found, it turns out that despite being neglected for many decades and not researched for many decades, this effect can be found actually in 1/10 of magnetic materials reported in magnetic database. So that means that although the effect came somehow sort of as a surprise, it still can have quite wide effect on the spontaneous research, for instance, and the spin splitting research. So this leads us to compare it to term introduced by Nassim Nicholas Taleb in a very nice book about this black swan, which are exactly such events in research, in finance, or in technology that comes as a surprise, but they have a major effect. So with this, I will start with a very simple introduction into the symmetries. And symmetries, as Phil Anderson, for instance, was saying many times, are at the core of physics. So the three most important symmetries in physics, because they impose the most constraints on the physics, are CPT symmetries. So besides the charge conjugation symmetry, which we will not discuss in this talk, we are left with time reversal symmetry and spatial inversion symmetry. So I denote time reversal by T and spatial inversion by P. Now I will take some energy bands like I had in the previous slides, and I will analyze how the symmetries are transforming energy band, its quantum index, the spin index, and the crystal momentum. So if I look in the Fermi surface in the Kx, Ky crystal momentum plane, and I look at conventional non-magnetic system, which has spatial inversion and time reversal symmetry, I see that they need to have Kramer's degenerate bands in the whole Brillouin zone. And the reason is that the time reversal reverses spins at the opposite momenta. Yeah? So it connects these two spins, while spatial inversion preserves spin at the opposite momenta. So this together is giving us the requirement of double degenerate bands in the complete Brillouin zone. Now, when we look into antiferromagnetic systems, so the most studied antiferromagnetic systems turns out to have the combined PT symmetry. Here I show one simple example. So if I take the crystal unit cell and I double it, and while here I have one orientation and here I have opposite orientation, I do not have anymore the original non-magnetic time reversal symmetry because there is antiferromagnetism, but I will still have time reversal symmetry which connects these two magnetic sublattices. So the symmetry here is actually time reversal combined with partial unit cell translation. And then on this blue one, for instance, you see that I have spatial inversion symmetry. So this together gives me Kramer's theorem in antiferromagnet. And this was studied, for instance, in these papers. From a recent work, people have focused on topological aspects in this class, and they were studying a lot manganese bismuth telluride, for instance. So 1, 2, 4 type of. And you see that here, if you would make a cut through its energy bands, you will end up exactly with this type of dispersion. So from this perspective, it looks like that antiferromagnets are not interesting for spin splitting physics. And we need somehow break either spatial inversion or time reversal symmetry or both. So to analyze how we can do it and whether we can do it, we went through all possible 1,651 magnetic symmetry groups. And I want to say that this is still feasible when you compare it to, there are many more order of magnitudes existing materials. So we said instead of analyzing and doing machine learning on all the possible materials, let's analyze all the possible symmetries. And here I summarize what classes we have according to this famous book on magnetic symmetries. So when we start with the non-magnetic symmetries without any time reversal symmetry, we have rotational symmetries, for instance, and mirror symmetries. And there is a relation between them by inversion. So when you apply inversion on rotation, you obtain mirror symmetry. And there is 230 of them. That's the known number from the basic condensed matter classes. Then when you add the anti-unitary operation of time reversal, you actually can just, put this time reversal to all of these elements, and then you will just double the symmetry group in this way, and you will have this type 2, which are the non-magnetic ones with time reversal symmetry. And then the most interesting ones for magnetism are these two classes. In this class, in the type 3, you actually choose just 1/2 of the elements from the original non-magnetic symmetry class, and you conjugate the other half by time reversal symmetry. So then you end up with this hybrid group, and this corresponds to not doing anything with your crystal unit cell. You just add to the crystal unit cell some magnetism. So for instance, example would be the antiferromagnets like manganese to gold or copper manganese arsenic. And then there is a fourth class, and these are antiferromagnets, for instance, where you actually have this partial unit cell translation combined with time reversal. So these are called black and white symmetry groups. And example is this manganese bismuth telluride from the previous slide, where you have this symmetry operation. So you take the original non-magnetic symmetry, you add this partial unit cell translation combined with time reversal, and then you double the crystal unit cell by the antiferromagnetism, and that means that you are halving the Brillouin zone, for instance. So if we look in terms of candidate symmetries, we see that we have 275 ferromagnetic symmetry groups of type 1 and 3, and we have 1421 of type 1, 3, and 4, which can be antiferromagnetic. And then those which, according to the previous slide, have spin degenerate bands are found in the type 3 and 4, and we call them Kramer's antiferromagnets. So we can break now either spatial inversion or time reversal in these symmetry groups in different ways to obtain some spin splitting. So let me start with the notoriously known examples of breaking spatial inversion, which was studied for many decades in condensed matter physics. So I am showing here bulk Rashba effect. So I have a crystal like bismuth telluride iodide. I'm simplifying here. The crystal is more complicated, but for the sake of simplicity, I'm showing just a honeycomb cut through such a system with two different atoms. And originally inversion sitting here is now not anymore symmetry because you have here two chemically different atoms. When you then look into a crystal momentum plane perpendicular to the symmetry breaking vector, you can obtain this spatial inversion symmetry breaking spin splitting. So you will have this typical well-known Rashba spin orbit interaction where the spins are winding around your Fermi surfaces. So you need heavy elements, and spin is not conserved number. And even in this, materials like bismuth telluride iodide, where people call it giant spin splitting, it's still of the order of 0.1 electron volt, as reported by Ishizaka in this paper. There is another possibility how to break spatial inversion symmetry, and that's when you break it not by the crystal structure, but by the magnetic structure. So you are not, changing the chemical composition, but rather you induce some magnetism. So in this case, for instance, I can induce this antiferromagnetism, and the original inversion center between these two atoms is now lost, is broken. So I have broken inversion, time reversal, but the PT is in this case still symmetry. So what happens is that I have still double degenerate bands, but they just shift in the Fermi cuts, okay? And this is what we call Kramer's antiferromagnets, and they can host, for instance, Dirac quasi-particles, as we have shown here. So this is obviously not a way how to do spin splitting physics with antiferromagnets. So let's try to break time reversal symmetry with antiferromagnetism. The most common way how to do it, how to break time reversal symmetry spontaneously, is obviously magnetization. So if you add magnetization, you have minority and majority channels, and you have ferromagnetism, which is inherently metallic because of these channels, and it produces dipolar fields. Another alternative mechanism of the splitting, which attracted a lot of attention in our community in the past 5 years, was this non-collinear antiferromagnets, which still can lead to a splitting, but spin is not conserved. So the spin, as was shown, for instance, by Jakub Železný in his PRL, is rotating along the Fermi surface in quite crazy manner. So it's following, of course, this non-collinear exchange fields. And as was shown by Hayame, this corresponds to the situation of magnetic octupole in comparison to this magnetic dipole in ferromagnets. And this brings me to the new possibility, which we will discuss today. And that's a possibility that you take the lattice, as from the previous slides of the collinear antiferromagnet, and you add there these non-magnetic atoms. And these non-magnetic atoms will actually break the spin degeneracy, and they will help in combination with the collinear antiferromagnetism to produce such a toroidal Fermi surfaces, spin-split Fermi surfaces. So here I can remind you the picture with the swans, because you see that the blue one can be transformed to the red one by this rotation, by this toroidal rotation. So we have here, in contrast to this case, we have spin conserved, and these systems are much better semiconducting candidates. And also this system exhibits magnetic quadrupolar symmetry in contrast to these two other splittings. So this brings me to our analysis, how to identify the splitting in material candidates and symmetry classification. So we start with simple, I simplified this derivation, but just to understand the basic concept. So when we study the magnetic symmetries, here I'm summarizing the important symmetry group classes. So I was explaining you now these 1651 magnetic space groups, and these are the space groups which in the end correspond to the material which you measure in the experiment. But if you want to study the mechanism, you can look at some more abstract concepts, and these are these free symmetric groups. So you can start with the very simple non-magnetic symmetric groups, which you construct by taking the symmetric group of your Bravais lattice of the crystal. And then you can add rotational symmetries and spin rotational symmetries, which are decoupled. So you are neglected spin orbit coupling, and you can have here also partial unit cell translation. So when you have such a symmetries, you will have very simple symmetry group, which will have quite high degeneracy. Then you can add spin orbit coupling, and you will obtain the conventional space groups. And then when you add on top of it magnetic ordering, so for instance, the antiferromagnetism, you will have these magnetic space groups I was talking about. But there is yet another way how to go from here to here, and that's that you will reverse the order of adding these interactions. So you can first add magnetic interaction and then spin lattice interaction. And this object, this symmetry group, is called spin space group. It's a symmetry class which was investigated much less in literature. And that's one of the reasons why actually the spin space group, which plays a crucial role in our antiferromagnetic spin splitting, this splitting was overlooked for so many decades. So now, being equipped with this basic vocabulary, I can share the symmetry criteria for identifying the spin splitting. So we need to have time reversal symmetry breaking. By that I mean I need representation in the crystal momentum space which allows spin splitting in the magnetic space group, but also in the spin space group. Okay, this means that if I switch off spin orbit coupling, I still need to have spin splitting which originate just from the magnetism, not from the spin orbit interaction. Then to produce this spin splitting by this Swanish anisotropic magnetization densities, I need asymmetry with atomic positions. So these are positions in the crystal where I put in the Bravais lattice, I put the atoms, and they need to be anisotropic. So one way how to make them anisotropic is to distribute by this crystal time reversal symmetry breaking mechanism, distribute these non-magnetic atoms in the crystal on a low symmetric positions. And now you can see that indeed these two atoms have different surroundings because these octahedra are actually rotated by this Swanish 90 degrees symmetry. And the last thing, practically what we require is that the integration over the spin densities is vanishing. And that you can see here. This is ab initio calculated, and details you can find here, how we do these calculations. But the important thing is that these magnetization densities are still compensated, although they are so highly anisotropic. So this was also discussed recently in paper by Rajba and Zunger. And we can now see how this anisotropic densities, which we have predicted 2 years ago in this paper, how they can lead to the spin splitting when we calculate it from first principles. So we have found material ruthenium dioxide, which attracted recently attention because it's a metallic antiferromagnet with 5D elements, where you would normally expect that it should be actually insulating. So if you look at its Fermi surfaces by DFT, you have this toroidally shaped spin split Fermi surfaces. So this material is an example which fulfills the symmetry criteria and which produces strong spin splitting. That the spin splitting is strong, we can see now on the energy band dispersion. So if I look, for instance, on these two bands, you see that the splitting is as large as 1 electron volt, okay? While the density of states is still perfectly antiferromagnetically compensated. And then when we look at the K.P model, which also people like Hayame and Rajba with Zunger were looking into, and we look at the gamma point, we see that actually the Hamiltonian, which captures this low energy physics around gamma point, can be very simple. So we have here the conventional kinetic energy, and then we add this new term where we have, instead of relativistic strength here, we have here exchange strength. That's the reason why this can be so strong. And then we have this toroidal type of splitting where we couple crystal momentum X, crystal momentum Y, and Z component of Pauli matrix. And this is also at the heart of having spin splitting, which preserves spin quantum number, because this apparently commutes with the spin operator. So there was also another paper by Professor Honza Kunesh, who was also discussing recently ruthenium dioxide. So this material seems to attract quite substantial attention. This brings me to explanation what happens when we switch on spin-orbit interaction, because spin-orbit interaction could possibly, in systems with ruthenium, which is still a heavy element, could spoil a lot of this physics. But it turns out that it doesn't. And this you can see on this spin polarization calculated from density functional theory, where I have not only antiferromagnetism, but I have now also spin-orbit interaction switch on. Okay, so on the previous slide, I had no spin-orbit interaction, and I have this 1 electron volt spin splitting. Now I switch on this large spin-orbit interaction, and I see that the spin polarization in large parts of Brillouin zone is still perfect. So these colors correspond to the spin polarization like in the previous slide. And if you look at the cut, the spin remains beautifully quantized. So that's something what people were trying to achieve in many scenarios. And one of the most successful, besides topological insulators with the problems I already mentioned, was, for instance, the Bernevik and Xu Chengzhang proposal of spin spiral, where they have tuned the Dresselhaus and Rajba for a special crystal momentum orientation, where you have such a compensation that indeed the Hamiltonian of the spin spiral state is commuting with the spin operator. Here you see that this beautiful spin polarization and spin quantization doesn't happen only for certain momenta, but actually for the huge parts of the Brillouin zone. Another comparison is that this effect is so strong because it's of exchange origin. We can compare it to the effect of the small net moment which arises in these systems, because these systems, due to these non-magnetic atoms, have also relativistic Jarzynski-Moria interaction. But because this effect is of perturbative relativistic origin, as was shown already 60 years ago, the induced moment is quite small. So you see that although there are some similar symmetry origins of these effects, because of the different microscopic mechanism, they have a very different scale. And another effect, which is beautiful consequence, which we discussed together with Jakub Žaluzný from Prague in our recent archive paper, and some other groups were discussing similar effects recently, is that this electronic structure can produce even transversal spin current, and the spin polarization in this spin current can be controlled by the null vector orientation. And that's something what is quite distinct when we compare it to the conventional spin Hall effect, where the spin polarization is given by the crystal. And it's very difficult to find external means how to control the relativistic spin-orbit interaction. In this case, we have the null vector, which can mediate the control of the spin interaction. And I want to also mention that next week, Professor Ingrid Mertig will give this online SPICE seminar series talk, and she will talk probably about some of these effects. So this brings me to the summary of the first part of the talk. And here I have a table where I'm comparing the strength of the spin splitting depending on a different mechanism. So here I'm showing which symmetries are broken or preserved. Here I'm showing typical material, here origin, macroscopic origin, and here the strength of the spin splitting. So this class are non-magnetic systems where we break spatial inversion. And then here are the strengths of the spin splitting. These are the record values. Then we have this conventional, or not conventional, but more common antiferromagnets now, which were driving the antiferromagnetic spintronics research in the last 5 years. And these antiferromagnets are Kramer's degenerate, so they have 0 electron volt splitting. And then we have this class of crystal antiferromagnets where the spin splitting can be extremely large. So for instance, to the one which I already have shown you, I can compare also nickel fluoride, and you see that the splitting in nickel fluoride is smaller, it's just 180 milli-electron volts, but this can originate from, as you can see here, from the anisotropy of these Fermi surfaces in nickel fluoride being actually less pronounced than in ruthenium dioxide. And there are several references which were also discussing recently some splittings in manganese fluoride or in organic systems, but the splittings are still much smaller, although the mechanism is the same as ours. The splittings are still smaller than in ruthenium dioxide. And last comparison I want to draw is that there are also systems where you still will have this anisotropic spin densities, but without spin orbit interaction, there will be still spin degenerate bands because simply the system doesn't fulfill the criterion 2. If you remember, that was the criterion with spin space group. So the order of the spin space group is simply too high. So you need add the spin orbit interaction to produce the splitting, and then you end up with the same physics essentially as here. So for instance, the paper by Silvia Picozzi from last year was showing that this antiferromagnet actually has, due to the bismuth, 200 milli-eV splitting approximately, but it's entirely due to Rashba. So it's very different to our crystal antiferromagnetic spin splitting. So I want to conclude this section with the back-to-back comparison of Rashba and this antiferromagnetic spin splitting. So I'm comparing here symmetry, origin, microscopic mechanism, crystal class, where we can find this effect, spin character, associated Hall effect, and low energy Hamiltonian. So in the case of Rashba, we have non-centrosymmetric systems with time reversal symmetry, and we need some heavy elements. In contrast, in this crystal antiferromagnetic spin splitting, we have centrosymmetric crystal with time reversal symmetry broken by the collinear antiferromagnetism, and we don't need these high atomic number elements because the splitting is due to the exchange mechanism. Here, we need Dykov positions and the overall crystal structure to take polar symmetry. Here we have magnetic toroidal symmetry. In the Rashba case, the spin is not conserved, apparently, while in this spin splitting by antiferromagnetism, it can be conserved, and it leads to the spin filtering functionality I was mentioning before. When we look at the Hall effects, here the most famous example is spin Hall effect and quantum spin Hall effect and topological insulators. And here I will explain in the second part of the talk that here one of the consequences is also a crystal Hall effect in the case of this antiferromagnetic spin splitting. And here I just compare that you can see that these properties are really manifested in these minimal models of the spin splitting. So this brings me to the second part, where I will talk about the consequence in terms of the crystal Hall effect in ruthenium dioxide. So let me start with brief introduction into spontaneous Hall effects. And here I would like to start with a sentence from Haldane's Nobel Prize speech in 2016, where he said that just knowing the correct laws of quantum mechanics does not mean that we understand all the strange phenomena that it allows. And what we are trying to do is quite similar, but we are studying relativistic quantum mechanics. And we don't want to just find exotic and strange phenomena, but maybe also phenomena which can be useful for demonstrating some proof of the concept nanoelectronics physics. So perfect example of such an effect which belongs to this category is spontaneous Hall effect. It was discovered already 120 years ago by Edwin Hall when he was like around 25, 27. And he found 2 years after his ordinary Hall effect, he found that there is additional contribution, which is order of magnitude stronger in ferromagnets like iron. And then people were studying it, and the history is full of twists and turns. But I want to say that if we study the symmetry of the effect, because it's transversal antisymmetric component of the resistivity, it can be, as was shown in many books, for instance, in Landau and Lifshitz, it can be shown that it corresponds to the existence of this Hall vector. So if we want to know whether the material has this effect, we just need to look whether the Hall vector is allowed. So this doesn't say anything about the strength of the effect or the mechanism, but it tells us whether this material is suspicious from this effect. And the most suspicious materials are obviously ferromagnets, because there the Hall vector is, the direction of Hall vector coincides with the magnetization. So for a very long time, it was believed in the papers that actually the anomalous Hall, the spontaneous Hall contribution is proportional to magnetization on top of the ordinary Hall contribution. Some recent developments in the microscopic understanding of this effect was beautifully explained by the Souza and Vanderbilt paper 5 years ago. In past 5 years also, Alan MacDonald, Claudia Felser, Stuart Parkin, Hua Chen, Professor Nakatsui, and other people have shown that actually this type of physics can be found also in non-collinear antiferromagnets without any net magnetization. So they have shown theoretically and later experimentally that you can have these complicated non-collinear structures which can produce the quite strong Hall signal. So you will have, experimentally, you will have additional contribution in your Hall resistivity. And when you get rid of these two terms, you will be left with this Hall resistivity, which originates entirely from the non-collinear antiferromagnetic ordering. So to summarize, I would say that the history of the spontaneous Hall effect can be classified according to 3 different efforts. One effort is symmetry analysis. Second effort is how microscopically we produce the spin splitting. And the last effort is, how we do spin-orbit interaction and how we produce the topology of the energy bands, which are producing this transversal Hall voltage. So starting with the more conventional theories and more conventional understanding, after this pioneering Hall discoveries of the effect, people were debating for a long time whether the effect originates from extrinsic scattering or intrinsic Berry curvature effects. To this end, it was a huge advancement by the discovery of quantum Hall effect and later shown by Jungwirth and Nagaosa that actually even the conventional anomalous Hall effect can be explained by the concepts promoted in the quantum Hall effect, and that's, for instance, Berry curvature. And the experimental efforts in past decade are indicating that there are indeed many materials where really this intrinsic Berry curvature origin seems to be dominating. And then in last decade, also people have identified diverse mechanisms depending on the magnetic ordering. So for instance, these works have shown that if you have non-coplanar magnetic structures, you can have something what people now call topological Hall effect, where you don't need actually the relativistic spin-orbit interaction, but rather you have something like scalar spin chirality, which substitute this. So the non-coplanarity of the texture is lowering the symmetry enough to produce the Hall signal. And then what I mentioned on the previous slide, the latest big advancement was this discovery of spontaneous Hall effect in non-collinear antiferromagnets. So this brings me back to the question and to our collinear antiferromagnets. So you have seen in the beginning that these non-collinear antiferromagnets still have some limitations. And for instance, you cannot have this beautiful spin quantization. So the question is, can we maybe, find some collinear antiferromagnets which would have the spontaneous Hall effect? And I will show you now that indeed we can. So we can apply the symmetry analysis. So we can analyze this Hall vector first, and it transforms as a magnetization. So it will be allowed in 31 ferromagnetic point groups. But that's, as I will show you later, the only parallel. The microscopic mechanisms are very different. Now, since we want collinear antiferromagnetism, I need to cross out symmetry groups which contain 3, 4, and 6-fold operation, which are not compatible with collinear antiferromagnetism. So I'm left with 14 magnetic point groups. And now when I take our rutile structure, I can apply our symmetry criteria to see where the Hall vector is or whether it's allowed. The first criterion is that if there is no symmetry, the whole plane does not have to be given by symmetry, and then it's arbitrarily oriented. So that's not this case because we have here some symmetries. And we have here these rotational symmetries and these anti-unitary rotational symmetries. By anti-unitary rotational symmetries, I mean that I rotate the crystal and I apply time reversal. So this rule tells me, the second rule tells me that I need to be perpendicular with the Hall vector to this anti-unitary symmetry. So I have here this and this anti-unitary symmetry, and I see Hall vector indeed is perpendicular. And then if I have rotational symmetry, the Hall vector needs to be parallel. So according to the symmetry analysis, we expect when we have the moments along this 100 axis in the rutile crystal to have the Hall vector along 010. I want to emphasize that although the symmetry criteria in the beginning are parallel to the symmetry criteria for net moment, the microscopic mechanisms are very different. So in the case of the magnetization, as I already mentioned, this is known for 60 years that you have relativistic Janshinsky-Moria interaction, and that's why the net moments are quite small. So in the case of this, we have shown experimentally that it's just 0.05 Bohr magneton per unit cell. In the case of the crystal Hall, the origin of the effects, the macroscopic origin, is due to the topological Berry curvature and local magnetization densities. And that's, as I will now show you in the last few slides, can be substantially strong. So we have obtained experimentally 330 Siemens centimeters. So I wanted to emphasize the differences. To calculate the Hall conductivity, I can start with calculating crystal momentum resolved Berry curvature. So if you want to see details of the calculations, you can look here. But the main message is that here, these anti-crossing features are producing when we switch on spin-orbit coupling together with the antiferromagnetic spin splitting, this large Berry curvature. And the spikes can be even stronger than in iron. Now, very interesting feature of this Berry curvature is that in this antiferromagnets we can control it. So I need for this crystal chirality. So if I have these two magnetic atoms and I'm jumping with the electron, I can put the non-magnetic atom either on this side or on the opposite side. And I can then define this local crystal chirality. So you see that if I jump like this, I have this chirality, but I can also distribute the atoms in the mirror position, and then this would reverse the crystal chirality. So when I calculate the magnetization densities for these two local chiralities, and I calculate the Berry curvature, I see that although the Nel vector remains the same, I have only reversed by this black swan operation, I have reversed the non-magnetic atoms in the shape of the anisotropic densities. This results in changing the sign of the Hall conductivity. So there's a feature which is not available in the conventional systems. If I look at systems which are not central symmetric, I can have this effect in its global variant. and people were studying this signal recently. This is something what is ongoing effort. It's a beautiful work where they have shown a huge signal, but it's not clear yet whether this mechanism is really this one. So then we need to make sure that our signal doesn't originate from the counting. So since these systems have this DMI interaction, we have decomposed the calculated whole signal into contribution from the net moment. This is what we call the sigma anomalous Hall effect, the conventional one. And then we have this one from the null vector, and that's this red one. And you see that for all these Canting angles, when we tune in the density functional theory, the Canting, you see that this crystal Hall contribution is the dominating one. And especially when you go to the zero fields, you see that there it's really like the only contribution. Recently, Yuri Mokrosov paper have shown that there could be some other contributions when the counting is important. I want to emphasize that in this ruthenium dioxide, it's not important contribution. And also the Hall vector is not proportional to sublattice magnetization, neither to net magnetization, as you can see by comparing these two pictures. So this brings me to last few slides on experiment. And I want to start with emphasizing that this crystal Hall conductivity can be, in contrast to the anomalous Hall conductivity in ferromagnets, can be hugely anisotropic. So when we take the cases I was describing so far, I have these moments along one of the main crystal axes, and then the system wants to count. But it is known already for 50 years from the Soviet literature that if you orient the moments along the 110 or 1-10, there actually is not generated counting moments due to DMI, but there is longitudinal DMI, and the system behaves more like a ferrimagnet. But still, in both cases, the main contributions we have checked is coming from the null vector. So you see here that not only the signal is anisotropic, but in this rutile symmetry, it can be even switched off. So when we rotate the moments along 001 orientation, the whole conductivity is prohibited by symmetry. So this is something what is not available in ferromagnets, and although Roman, Mokrosov, and Souza discussed already 10 years ago that in certain low symmetric ferromagnets like HCP cobalt, we can have the strong anisotropy. You are never able by symmetry switch off this effect because you have the ferromagnetic moment always available. So this brings me to verifying these ideas in experiment. And to this end, Zhikui Liu and his team has delivered impressive experimental investigations in terms of beautiful growth of layer, which was exactly needed for this type of experiments. And then they did an amazing experiment. So let me just give you a brief summary. So Zhikui and his friends did two types of layers. So they have grown this 110 ruthenium dioxide on MgO and ruthenium dioxide 100 on STO. And then when they measure the longitudinal resistivity, the systems are identical, and you have all the current going through this ruthenium dioxide. Now, because the ruthenium dioxide is known from the PRL papers from 2017 and 19 that the easy axis is close to the C axis, so it's actually close to the axis where there is no Hall signal. So we need somehow to put the null vector into the orientation where there is some non-zero projection. And that indeed he was able to achieve by beautiful high magnetic field experiment. So he put the external magnetic field perpendicular to the layers. And what is known for a very long time, also from the Soviet literature, that then you have very complicated dynamics of this null vector because you have coupling to the magnetization and to the null vector. So what was happening is that in his experiment for this configuration, he was able to measure beautiful Hall resistivity, and here we are showing actually the data after subtracting the ordinary Hall effect contribution. When one subtracts the ordinary Hall effect contribution in this configuration, there is no or there is vanishing small Hall signal. So this is consistent with the prediction that this crystal Hall conductivity is highly anisotropic. And when we recalculate the Hall resistivity to Hall conductivity, we see that it can be large as 330 Siemens centimeter. And then on top of it, when the crystal structure was much less, was more poor, then the signal vanishes as well. So this is strong indication, these results are strong indication that indeed his signal originates from this mechanism I was talking about today. And when we compare it to our theoretical calculations, we see indeed that there is this strong anisotropy. So when we look, for instance, here, you see that there is a suppressed signal, while there is a quite strong signal for the 110 configuration. And it's also consistent with this easy axis calculated along the 001. Yeah, so the system really prefers to be here. So that's why we need the external magnetic field. But I want to emphasize that when we calculate the energy bands in the Zeeman strong magnetic fields, you cannot see any differences by naked eyes with the energy bands, because they are already so splitted by the antiferromagnetism that the magnetic field has no influence on the electronic structure. The only thing what it does in this experiment is that it's tilting the moments from the axis where the Hall effect is prohibited to the orientation where the Hall effect is allowed. So the last feature which we see here is that there is some suppression of the signal, and this can be attributed actually to tuning the electronic correlations, which roughly simulate the effect of temperature. So when the net moment is decreasing, what you can see that actually the crystal Hall conductivity can abruptly go down. The reason here is that simply for the small values, there is no antiferromagnetism, and for the large values, the system gets insulating. So this brings me slowly to the end. I want to emphasize that surprisingly, this effect, as you can see from this table, can be found potentially in many systems. So to read this table, T is time inversion, P is space inversion, M is mirror, and this operation is this combined spatial inversion and time reversal. And here I have picked just a few interesting candidates. When I analyze all systems in the magnetic database, what I see is that actually 1/10 of all these materials is compatible with this effect. And indeed, surprisingly, already many other interesting papers appeared on different materials and different aspects of this type of effects. Also, in retrospective, some effects which were originally attributed to skyrmions or some other mechanisms could be eventually contributed by our crystal Hall effect, for instance, the systems in these papers. But this is open issue to see which contribution is really the dominating one. So to summarize the spontaneous Hall effect in antiferromagnets, we have now 3 contributions: the topological Hall due to the non-coplanar structure, the anomalous Hall due to the non-collinear structure, and the crystal Hall due to the collinear structure. So you can see the pattern that if we go in this direction, we have more complex magnetic ordering, which is more difficult to control. And when we go into this direction, we have more interesting spin-orbit interaction complexity. And here I also compare to show you that the most common systems are actually, in the terms of crystal Hall, the strength can compare or can be even larger than in the more conventional topological and anomalous Hall. So I see that I'm running out of my time, and let me conclude with 3 brief messages. So we have found third fundamental spontaneous spin splitting without magnetic dipole due to the anisotropic magnetization densities from the crystal time reversal symmetry breaking by the non-magnetic atoms and collinear antiferromagnetism, as we saw on these densities and the splitting. Then we have predicted and observed the crystal Hall conductivity of quite strong magnitude in ruthenium dioxide antiferromagnet. And this is telling us that maybe there is some paradigm change going from exchange ferromagnetic or external magnetic field effects studied in 1980s over relativistic effects studied in 2000, 2010 to collinear antiferromagnetism induced effect. And by this, thanks a lot for your attention, and looking forward for your questions.
Thank you, Libor, and then to everybody, thank him. I guess your hands up is for thanking. I guess that's the only thing we can do here. So now the talk is open for questions. I think there's lots of hands up of saying thank you, but now take them down, and then if you have a question, keep your hand up. I will allow, I guess, I think Igor. Igor, go ahead. You have a question?
Yes. Actually, more like comment than a question, a bit of self-advertising. Just in addition to this core mechanism for spin effect in that what you were, if you show the slide before. Now you were listing somewhere, you were listing 3 mechanisms for Hall effect. I would add to that we recently proposed a 4th mechanism, which is entirely due to spin fluctuations and appears in structures that do not allow for topological Hall effect, but demonstrated through order by disorder, like pneumatic thing. And the other comment is that in addition to this beautiful explanation about how different chirality of non-magnetic atoms generate this effect, we recently noticed that there is symmetrically equivalent but physically very different mechanism where your structure, and such structures exist, consist of dimerized magnetic atoms which order antiferromagnetically internally, and yet because of how they are embedded in the entire crystal, they also demonstrate this crystal anti-Kramer's effect that you discussed, which I think is interesting material science option. That's all. Thank you.
So thanks a lot, Igor. These are beautiful comments. I agree there are more mechanisms. I just constrained myself here to those which are really of intrinsic origin and are in antiferromagnets. So I believe that if we go beyond this realm, there could be even more mechanisms.
No, the mechanism that I described, that you know about that, you know that paper, that's actually within this realm. So it's antiferromagnetic, but it requires external magnetic field.
Yeah,
that's the difference.
Yeah, how is it spontaneous versus the other one?
Yeah.
So I would say that it's like I also didn't mention the materials like zirconium pentatelluride, where you need the magnetic field to split the bands, for instance, and then you have it quite large because Saba claims that it originates from the topology of the band structure. There is this few years ago Nature Physics paper on it, or these materials like gadolinium, platinum, bismuth, where the effect originates from the canting of the antiferromagnetic order. So I was here really constrained myself to effects where the spontaneity is important.
Okay.
Yeah, but thanks a lot for a great comment. And also, if you want to discuss in more details privately, I have many more comments, and I enjoyed our discussion last 2 weeks.
Oh yeah, I hope to continue that.
That's right. It's always a good joke as well. All right. So Gisela, you have a question?
Yeah, I have. Can you hear me?
Yeah, we can hear you.
Okay. So I have a question. Your fantastic band structures, they are all related to perfect crystals. And in nature, and if you compare it with measurements, you have a natural crystal which has defects probably in a normal single crystal any 10 nanometers. So can you account for this, that there is some hole or some defect or some grain boundary which you will not see in macroscopic crystallographic studies?
Thanks. This is a very nice question. So this gives me opportunity to talk about our other efforts, and I will just mention 2 brief remarks. So one is that we also studied these things with coherent potential approximation, where we can include some type of defects. And then very often, of course, as we see in the experiment, these effects get suppressed. So that's negative message, let's say. But there is a positive message, and we found materials where actually the defects do not play such a role, and we actually are almost at the point to submit this to arXiv. So we can also discuss it when this will be on arXiv.
What crystals are these?
Yeah, so this is something we are working together with many people on, so I cannot.
Okay.
Yeah, but it will be available in 2 weeks, so
okay,
then we can discuss it.
I think Gisela, he's happy to send it to you privately, but not the 250 people want to hear it.
We can Skype if you want. Thanks a lot for the comment.
Okay. Let's see. I think Jan Mazel, you have a question. You can,
no, sorry, I just forgot to lower my hand again.
Oh, okay, sorry. Let me actually, Jacob Gerhard?
Yeah.
Right.
I have a question because you calculate for a single crystal where you have a given chirality or crystal symmetry. But if you grow this on strontium titanate, which does not have this chirality, and in the experiment you have millions of grains which start growing at different positions. So the film should first have a mixture of all possible crystal Hall symmetries, at least before it sees any field. So do you think the magnetic field then aligns this all to one crystal Hall chirality?
So again, beautiful question. Thanks a lot, Gerhard. This gives me opportunity to explain more on why we don't see the signal here. So what you just described is also contributing that when we have ruthenium dioxide, as you rightfully so said, on strontium titanate, we see that the signal is suppressed. So that's also possibly due to exactly what you said. So you have there plus minus compensated. But in the case of MGO, it doesn't seem to be the case, and there goes a big respect to the layers which SPICE produced.
Let's see, I don't see any farther hands up. So I think with this, Revas, yeah, it's okay. So yeah. Revas, you're back from yesterday, so it's the second time you get to talk. Go ahead, Revas.
Yes. Thanks again, Libor, for another beautiful talk. Two questions, both of somewhat generic nature. First one, you showed us, you compared, for instance, the Zaloshinsky-Moria effect with the curvature effect in one of your transparencies, and but sort of the units were different, and somehow it may be helpful to make units the same, because otherwise it's comparing apples and oranges.
Yeah, so that's beautiful comment. So it is always comparing exactly as you say, apples and oranges. But very often when we are presenting this work, people are getting confused that they think that is the same thing as just having allowed magnetization and DMI. So I wanted maybe deliver, but didn't want it to say this, exactly what you are saying. So
because it would be helpful somehow to look at precisely the same quantity related to the effect, and then you would make units the same, and it would be very illustrative.
Yeah, so you are right. So for instance, what I could show would be the exchange strength here corresponding to the splitting, and I can have in electron volts, and then I can have in electron volts the net moment. So that's a very nice comment.
Yeah, and another question is towards the end, when you showed us a table of materials, how many, like what fraction of them roughly are conducting, and what fraction are insulators?
So the fraction is like 3 to 1 in a disadvantage of metals. So that's also possibly why the effect wasn't just randomly spotted, because a lot of these systems are insulating, but still, you know, in the insulators, you can find some versions of it, some, for instance, optical, and there is now a paper by Yuri Mokrosov about crystal magneto-optical effect. So, yeah,
and then there is an issue of how easy those insulators are to dope. But yeah, that's a separate story.
We have actually effort with also with Gerhard Jakob and with Matthias Kloy in this end. But then, as Gisela pointed out, there are also some issues with it that it's spoiling partly the signal. So this is ongoing. This is ongoing effort, of course.
Okay.
But thanks for the comments. Also, thanks for the comments yesterday. I was happy to read your PRL, and
Yeah, it's
added here. I added here. I hope that you see. I added
thank you. Yes, thank you. Very kind of you. Yeah, there are lots of similarities because also the effects I mentioned to you, they appear without any intrinsic spin-orbit coupling.
Exactly, but you still need the magnetic field, so that's why I'm emphasizing that.
Yeah, that was mentioned in the spontaneous.
Yeah, yeah. Thank you, Libor.
Welcome.
Thanks a lot, Revas.
So there doesn't seem to be any more questions. So I would like everybody to raise their hands up to thank again Libor for this short minute substitution and wonderful talk, and also for leading all these efforts and new ideas that in the field. And we're looking forward to many more predictions that you will have to teach us. Okay.
Thanks a lot, Jairo.
I thank everybody else. Oh, the panelists has a question? No, they're just waiting for saying okay, thank you. So with that, thank you, everybody. And